Anyway, so all right. Where am I even doing? I forget. So yesterday we looked at how to use the calculator a little bit, and today I want to look at it a little bit again. And I think what I showed you yesterday was probably not an efficient way to do things with the calculator. So let's try to come up with something better. Did they not give us food today? Nope.
They do that. This is like the third time it's happened.
There was 1 week where it was a whole week.
Oh, so this is like the 6th time it's happened.
They did it like the last 2, and then they just stopped. They just really run out. Because there's only like 2 back there.
They run out. They didn't have enough there. I see the 6, like all the way down the hallway,
And then no one else has it.
Well,
All right, I'll try to remember to
no
email
one else has it probably.
one of the assistant principals again and say, hey.
Oh, yeah, but they have it. Oh, they do. They do.
Okay.
I think they just hate us.
I think they do. I think it's because, what the hell? We don't always eat lunch? Alright, you have the next one. That was 1.8.
He gave me the same one.
Thank you for egg, Noel. That's great. All right. So let's look at another example with the calculator. And let's say we'll use the equations y1 equals x squared minus 2. And y2 equals, that's not
X squared.
I'm sorry. I meant x squared minus 1. And this will be negative x plus 2. So, the first thing you would do is you would get out your calculator and turn it on. So, hopefully you do that. And if it's dead, is that Sadiq? Hey, Sadiq, what's up? How can I help you?
Freaking bro right here. Best math teacher ever in the world.
I give you a handshake, but what did you do to it?
One hug, bro. Missed you, Gabe.
Well, he's
Good to see you. How did you find me?
I'm just looking for apple juice.
Oh, you're looking for apple juice and you just happen to come in here? It was good to see you. They didn't give us any food today, so
Why not?
welcome.
They neglected your class?
Again, yeah. They don't like us.
Should file a lawsuit.
It's too much work.
Alright, bro.
All right, see you, Sadiq. That was so cute. So you guys, did I tell you guys about the day that I had a student talk about like the that's a green marker up there? It's like, no, that's clearly red. And yeah, that's him. All right, that was that guy. He was in my last normal Algebra 1B class before COVID destroyed everything. All right, so anyway, back to here. You got y equals x squared minus 1. You go ahead and you graph that, x squared minus 1. And then you got your other equation, negative x plus 2. You go ahead and you graph that, negative x plus 2. And then you hit the graph button. Graph. Whee! And then you say, all right, maybe we should zoom out because it looks like they're going to intersect again further up here on the left, and we can't see that. So let's reset the viewing window. You go to zoom and Z standard, and that'll reset your viewing window to normal. Ta-da! And now you can kind of see what you need to see. Hooray! So you can see there's 2 intersection points. So you need to find what those 2 intersection points are. You can do that with a calculator by doing second trace, and then you're going to do a lot of stuff in second trace land. You can find, this is going to be where you find integrals. You can get derivatives here, but we want to find the intersection point. So that's option 5 on my calculator. Move the blinky dot over to that first intersection point. Hit enter 3 times. And that'll tell us, hey, these things intersect at x equals 2.30-ish. So I'm going to write this down, say x1 equals 2.303. That's a good point. It is negative. That's important. 4 point. Only because it's only because what? Oh. All right, board point Javier. Then you do it again because you can see there's another intersection point. So second, trace, intersect, option 5 for me. Maybe it's something different for you. Move the blinky dot over using the left and right arrows. And hit enter, 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 enter. And you get 1.303. 1.303 for that solution. And that's probably good to write down as well. So that's going to give you the bounds of integration. Now, what I told you guys yesterday was to, at this point, go back into y equals and like combine these two things together. And I decided, you know, maybe that's not super efficient. If you want to do that, that works. You can say, well, the top curve is the line, and the bottom curve is the blue. So if you did it that way from yesterday, you would come back here. Top curve was the line, bottom curve was the parabola. So you would take this thing and just type it down here as a minus x squared minus 1 in parentheses. But if you don't want to bother with that, what you can do here on the graph is just integrate over this interval given by these 2 points for the red line, and also integrate over those 2 points for the blue, and then subtract those 2 results. And maybe that's more efficient. So you take 2 integrals and then just subtract the 2 integral values. So if you do that here, you say second, trace, integral. Now, you got to know, who am I integrating on? Am I integrating on red or blue? And the way you tell is you look up here, and that tells you which equation you're doing. So this is x squared minus 1. That's the blue curve underneath. I want to do the red curve first. So to switch curves, I use the up or down buttons. So up or down buttons lets you go back and forth between the curves. Left and right lets you move the blinky dot on one of those curves. So if you want to travel along the red line, click the up or down arrow. Now you're on the red line. You can see that which equation you're on is up there in the corner. And then you can move along that line using the left or right arrow. The lower limit we said was negative 2.303, so we'll just type that in here, negative 2.303. Hit enter. My upper limit we said was positive 1.303, 1.303. And hit enter, and that is 9.015. So what I would do is I would say the area for the top is 9.015. Then you do the same thing for the bottom equation. You get that integral. So you say second, trace, integral is option 7 for me. And now I'm going to be on the blue line. Make sure I'm on the blue curve. And do the same bounds of integration. So negative 2.303. Enter. And then 1 point, nope. Nope. Hit the right dot. There you go. Can't do anything right. 1.303. Yeah, I realized I could do that. And that's 1.2029. And then you subtract it, because you do integral. A normal integral is integral of the top minus the bottom. And because they don't switch positions over this interval, it's always the red line on top and always the blue line on the bottom. We don't need to worry about having to switch. We just get integral of the top, integral of the bottom, and subtract them, because integral of top minus bottom is the same as integral of top minus integral of bottom. You can break this into 2 integrals because it's subtraction, not multiplication. And when you subtract these, you have 9.015 minus 1.203, and what is that? So 7.812. So that's the area between the 2 curves. Any questions with that? Michaela? Yeah. Like down here.
Yeah.
Yeah.
But
when we So-
subtract, it's fine.
There was red here and it's been covered up by blue now. So this red area is all this triangle. And then we're subtracting away the blue. And then we're left with this stuff that's still red. And that stuff that's still red is the area that we're looking for. So that's the area that's still red is the 7.812. So we're subtracting this. I think I understand what you're saying. Now I'm confused. Congratulations. What if we went back over here to the graph? Now I'm second guessing myself. So to make sure that I'm not lying to you, let's do yesterday's method, where we come back here, we said on this interval, the line was on top. So he's top, and then we'll subtract the x squared minus 1 equation. And then we'll get rid of this guy and graph it. And then we'll do the same bounds of integration because these that we found, the intersection points, are now the zeros of this new thing that I made. So if you do second, trace, integrate, option 7, from negative 2.303 to positive 1.303, this should, unless I screwed something up on the first example, should be 7.812, is it? Hooray! All right, so I didn't lie. So you can either, if you're doing this on the calculator, do it one of these two ways. Do it the first way that I showed you just today, where you do two integrals and then subtract them. You do the integral of whichever thing is on top, do the integral of whichever thing is on the bottom over the same interval, and then subtract those two values. Or once you've identified who's on top and who's on the bottom and where they intersect, go back into y equals, combine them by subtracting them in the appropriate way, and then get the integral here using those same x values, and then that area will be the what you're looking for. And I think I have them both spelled out as well as I was able to kind of word it. Hopefully the wording is clear on these notes, so you can refer to these as you're using your calculator for doing this stuff. No. I don't know if one is more effective than the other. I think they both have their strengths and their drawbacks. So whichever one you are more comfortable with doing for yourself, that should be what you do. What gets really annoying, and it's really annoying whether you're doing it by hand or with a calculator, is if the curves switch positions, and then you have to break this up into two separate intervals, and then you just got to be really careful about doing that. Any questions with the calculator work? Does anybody still need a graphing calculator? Everybody here has one? No, you don't? Does Lucy have one? Where is she at college? She's in the city, right? So that's pretty close. I was just going to say, like, go break into her dorm or wherever she's living and just steal it. What is she doing? Like, what is she studying?
I don't know. With this, like, you can grab calculator for that.
I don't know if you'll need a graphing calculator for that. So
I think she does.
maybe you should just invest in your own or something. I don't know. I'll try to have like just a couple of graphing calculators in here on a regular basis, but other teachers need them as well, and I can't get a whole class set. I can't justify that for like 4 people. But I'll see what I can do. I used to have my own extra graphing calculators, but they've all broken over the years. All right, so let's look at what if we have to do things in terms of y. Sam, could you please turn the light back on?
Well, you see, being over is better. So my brother is way smaller. Yeah. My brother is younger, right? How can he see? He has it. Yeah. And how old are you? Born at Betty. How old are you? Born at Betty.
Yes.
You know, I think I figured out why I was doing it. So it's subtracting the parts where it overlaps, but under the x-axis it didn't overlap.
Yeah. That's why I was confused as well. But it works out for whatever reason. All right, so find the area between graphs of x equals 3 minus y squared and x equals y plus 1. All right, so first of all, you're looking at this and say, wait a minute, I don't like this. Why don't I like this? X equals. Yeah, I don't like x equals. I don't like x as a function of y. All my life, I've dealt with y equals function of x, and by all my life, ever since like algebra 1. But now this is weird. So it's going to be like, everything is going to be sideways from what you're used to. So sometimes solving for y works, but not always. So let's just deal with it the way it's presented. It's usually presented to us in a certain way for a reason. And usually the reason is for convenience sake. Once in a while, the reason is to screw with you guys. But most of the time, the reason they present it in a certain way is for the sake of convenience. So let's just trust these people who gave us these equations and say, all right, I'll trust you guys. You want to seem to do things in terms of y, let's do that. So it's helpful, again, to make a little graph. What shape is this first guy going to be? Sideways parabola. And if you plug in 0 for y, what do you get for x? 3. And then, because it's negative y squared, it's a sideways parabola, would you expect this to open to the right or open to the left? Wouldn't it open to the left because it's a negative y squared?
Yes.
Like if it were negative x squared, we'd open down, right?
Yeah.
So in the up-down direction, down is negative.
Yeah.
In the left-right land, left is negative.
Yeah.
So y is
Oh, it's negative.
negative y squared. Shouldn't it open to the left?
Yeah.
So if you're not sure, we could always just plug in another number for y. Like plug in 1 for y. 3 minus 1 squared is... What's 1 squared? 3 minus 1 is... So you plug in 1 for y, you get back 2 for x. And same if you plug in negative 1 for y. Negative 1 for y gives you back positive 2 for x. So you have one of these jobs. Bethlehem.
What's called? Are we just like finding points on the graph without know that?
Let's just get the graph first. One thing at a time.
Wouldn't we
One thing at a time.
find that after that?
Maybe. All right. Y equals x equals y plus 1. Plug in 0. What shape is this going to be? A line. And you have an x-intercept at 1. And then I don't want to think about slope because I don't know how slope is going to work when it's turned sideways. So
Can't we just make that equal y? That wouldn't be that hard.
that's true. That would just be y equals x minus 1.
Yeah.
All right, so it's going to be like that. So all right, so if you just had to live with the graph, what would you guess are the points of intersection? 2, 1, and this looks like negative 1, negative 2 maybe. But if you want to be absolutely certain, and if you don't trust your graph because it's kind of too rough of a sketch drawn at freehand, set the two equations equal to each other. Say, all right, 3 minus y squared equals y plus 1. Let's get everybody on the same side. So add over the y squared, keep the y, subtract the 3. and you get y, what is it, plus 2 and minus 1. So you get y equals negative 2 and y equals 1. So that's what it looks like here. So you get negative 2 up to 1. If we were going to look at this vertically speaking, if we were going to do this in terms of x, who's the top curve? Like if we're going to do this top versus bottom like the way we've been doing so far, who's on top? The parabola is on top, but is that, like, what's the reason we want to find?
No, the line's not.
This thing, right? So we want to find this area right here. So for this area, who's on top? The line until you get to here, and then who's on top? But also who's on the bottom? Also the parabola. Okay, that's why we're doing the sideways. Because if we try to do this up down, the line is the top part from negative 1 until 2 for x, and then from 2 to 3, the parabola is both the top and the bottom. That's a little yucky. So this is where, okay, let's look sideways. Sideways, who's to the right? Who's to the left? Always?
Wait, I'm looking
Yeah,
at it on the
all right.
side.
So on parabola, in parabola land, what the hell am I talking about? In sideways land, the curve is to the right and the line is to the left all the way through. So like right here, line left, curve right, line left, curve right, line left, curve right, line left, curve right. All the way through, the line is to the left and curve is to the right. So for us, if we're going to do things in sideways land, instead of top minus bottom, we want to do right minus left.
Oh, right.
Because it's sideways. So in sideways land, we do right minus left instead of the usual top minus bottom. And here, we much prefer this, because if we try to do top minus bottom, we have a section where the top and the bottom are both a parabola. We'd have to create two integrals, one for when the line's on top, and then another for when the curve is on the top and the bottom, and dealing with that's a pain. So we're going to do a sideways kind of view of this. So we say area equals integral. Because we're doing things sideways, we're doing everything in terms of y. So what's our lower bound? Negative 2, and the upper bound is 1, because we're doing things all in terms of y. And then the right curve is the parabola. That's 3 minus y squared. The left curve is the line, so y plus 1 that you subtract. And then we don't usually use it, but except when we have to do a u substitution, we do. What's going to go on the end here? dy, not dx, because we're doing things in terms of y. So on an FRQ, if you set this thing up and you said it's all built beautifully, and then you tack the dx on the end because it's force of habit, minus a point. Michaela? Yeah. So I knew multiple people would probably do that. And so I knew I got to bring this up because it's an easy thing to do. You're so used to doing everything in terms of x, you're probably going to put a dx on the end without really thinking about it. When you're in terms of y, everything is y. The bounds of integration are based on y, the variables are y, and then this, whatever you call this thing, the differential at the end is dy. Other than that, from here on out, it's pretty much the same as what we've done before. You would say, all right, I'm going to have integral from negative 2 to 1, clean up the inside to have a negative y squared, and a negative y, and a 3 minus 1 is usually 2. And then you integrate. So what does negative y squared turn into? Negative 1/3 y cubed. Minus y becomes negative 1/2 y squared. 2 becomes 2y. And we're doing this from negative 2 up to 1. So doing the 1 first. Moderately disgusting. Plugging it in is easy. Evaluating is a pain. So what's our first term? Negative 1/3. Our middle term. Our third term. 2. All right, that was easy. It'll be annoying when I have to go back and do it, but plugging in the 1 itself is easy. All right, plugging in negative 2. A little annoying. What's negative 2 to the third? Negative 8 times negative 1/3. 8/3. -2 squared is 4. -half of 4 is -2. 2 times -2 is -4. And then you have fun going through that. I would probably distribute the negative first and combine like the thirds together. So I have -1/3 minus a half plus 2 minus 8/3 plus 2 minus 4. So -1/3 and -8/3 become plus 4. All right, so thank you. -1/3 and -8/3 makes -9/3. We call that -3. Plus 2 plus 2 plus 4 is plus 8, and we're minusing a half. So that becomes 5 minus a half. 4.5. Didn't we have an answer like this yesterday? Yeah, it's literally the same thing, just turned sideways. So,
Yeah, I don't know why you don't.
This thing?
Instead of combining on the same thing, I mean,
oh, instead of getting a common denominator of 6, why am I doing it this way? Because this way is easier for me to do in my head. Because I'm getting as much whole numberness as I can, and then adding or subtracting a half is easy.
But what if the 1/3 and the 8/3 make like a fraction? Then you have
Like, what if it was plus an 8/3 and you had like 7/3?
So much more work.
because then you. Just
Well, then
make it
that
all
would be
over the same
annoying.
thing.
Then I would go to your
You would have
method.
to do it anyway.
Then I would do the U thing. But I'm looking at this and seeing, well, that's a -1/3 and a minus 8/3. That'll make -3. So I'm trying to keep things in my head as much as possible while I'm up here. But
I feel like I would miss it on
that's easy to, yeah. So go ahead and write it out. It's fine. I don't care. Now, do you want to go back and redo this thing
No.
in terms of x?
No.
No, let's do that. All right, I think it'll be a good exercise. I love it. Yeah.
And then you make the
Yeah, what's going on?
No,
I like
let's
to
do
make you guys
that.
feel like you're a part of the class.
But we're not.
It's like Putin. Would you like me to invade you guys, Ukraine? No, we'd really rather you not. All right, I'll see you guys next Tuesday. So we probably shouldn't make jokes about a war that's going on right now. But, no, that wasn't cool. All right, so please don't fire me. So we have the same graph as before. So we have -1 comma -2, and then
Would you get 7 integral at
Wait, we're graphing it again.
because we're doing
We're doing it.
I'm graphing it again for the benefit of the people at home, so I don't have to keep pushing the button back and forth Keep referring to this thing.
Why?
So this is 3,
Oh,
and I don't think so.
What's the benefit?
I guess I could have just erased all that and started over.
Yeah, you better.
Too late.
So,
No, this doesn't concern you, okay?
what did it just
Wait,
not
you
be
so you're
possible
copying
to do, like,
Yeah. No, I'm just redrawing this thing, but I'm cutting out the things that aren't super important.
Why don't just
All right. Okay. So we have next shuffle. So,
you consider these a prize.
concern me too.
Are you getting paid?
Yes.
Yo, relax.
So we have x equals y plus 1. So if we're going to do things in terms of x like normal, what do I have to do with this equation? Yeah, rewrite it so that it's...
But then that changes your graph.
No, it doesn't. It's the same graph.
Right.
No, it doesn't.
Wait, what?
Y-intercept is -1, slope is 1/1. All right, and then the parabola thing, we had, what was it, x equals 3 minus y squared? So, right, add over the y squared, subtract the x, and then square root of that, we have y equals what? Yeah, and the plus or minus is important because the plus or minus is what gives us the upper half and the lower half. So the plus gives us the top half of the parabola, and the minus gives us the bottom half of the parabola. And then that's going to be key for this section over here. So we would have this area here that we're looking at, and I'm going to break this up into.
Wait, so at 2, what happens to the other graph? What happens to x minus 1?
Yeah. So as we look at this, who's the top curve from -1 until 2? The line. So we would have an integral from -1 until 2, where the line is on top, x minus 1, and the parabola is on the bottom. And what part of the parabola is underneath here? Is it the positive half or the negative half? The negative half. So that further complicates things. So no, but I really want to drive home. Learn to love y, because sometimes x will hate you. So I just wanted you to see how awful this can be. Just setting it up. We're not going to solve it. Just setting it up. No, you really need to see this. This is important. I've already committed. I've drew the picture. We're doing this. All right. So this is the lower half of the parabola. So when you subtract the parabola, you're subtracting the negative half. So you're minusing a negative square root of 3 minus x.
How do you know where it like stops being negative?
Because it's positive, negative.
For the other half, then you do the positive half minus the negative half.
Yes.
That
All right.
makes sense.
So once you get to x equals 2, the line is kind of out of the picture, and now the top half is the top half of the parabola. That's your positive part. And the bottom half is the lower half of the parabola. That's your negative part. And you could obviously like combine these and say these are the same thing. Minus minus is a plus. This becomes 2 root 3 minus x dx. This you can simplify as well, because minus minus makes a plus. You'd have x minus 1 plus root 3 minus x dx. And then, even if you set this up correctly, and you're like, oh no, this is no big deal, I can set this up, setting up the integral is easy, good for you. Even if that's the case, this is still going to be a pain in the neck to like integrate, because now you have to do like a u substitution on this square root to integrate that. So I would recommend when they give you things in terms of y, it is annoying because you're not used to that, but it often beats the option that would be x. So if they give you stuff in terms of y, there's probably a good reason for it. Yes, Sam?
So the second interval from 2 to 3.
Yep.
You're not like, because it's the area of, I guess, in between the two, but like the parabola, like the line isn't there, so you're just finding the area of the parabola.
Yeah. You're just finding the area of this section right here. So the section I shaded in red, that's the second integral. The section that's shaded in just purple is the first integral. Bethlehem?
Would it be wrong at 2 instead of finding just the parabola you found above the parabola in between the two graphs?
Like up
Yeah,
here?
yeah. You get it?
So if I found this
But
area,
that's in between graphs. That's not technically in between. You get it?
okay.
Oh, yeah.
So I'm saying that goes back to the language. I was being lazy and not writing out the full, here's what I should have written. Find the area of the region bounded by the graphs of, and I got lazy and thought I would shorten that so I'd have less to write, but you being the little lawyer that you are found the correct, I'm gonna like,
So you're not
find a
supposed to
loophole.
do that?
No. We did what I wanted us to do. She's nitpicking that word between.
I'm not nitpicking.
No, she's nitpicking.
I'm not.
She's got a point. She's got a point. I should have written it the way it should be written. You're right. I should have written find the area of the region bounded by the graphs of. But Diane had a question. Can we use the calculator to evaluate these integrals on the homework? Yeah, sure. It's good practice for the calculator. You guys need to know your way around the calculator, so practice that. You also need to be able to do stuff by hand. So maybe don't do them all with a calculator, but when you have something like this, yeah, just go to the calculator, evaluate it. But show the integral that you're setting up. somebody had a hand. Javier, did you have a hand? No. Sam had a hand.
So back to Betty's way, right? So if we were to do it, like, if the question asked us to find all of the area, so like we had to include that, what would you do? Would you, the line would be on top again, and then how, what would you subtract?
So I think you would do this thing the way it is, and then you'd have a third integral,
Yeah,
also from 2 to 3,
yeah.
line on top, and the top having the curve on the bottom.
Oh, if it said you see the graph, you still leave it right there.
Oh, so you're saying you need this, because this is the curve between itself.
Yeah.
I suppose you could argue to take that out.
But I'm wrong though?
Well, in the context of a test, I'll be much more careful about the language I use to like give you the prompt. So
So wait,
this should be an odd issue.
this right here.
But you're very good at reading.
Oh my god, yeah.
How do you set up the integral?
What?
How do you set up the integral? Because the line would be on top, right?
something like that.
Yeah.
So it'd be dash minus. But then what do you?
I guess if we're doing all of this area from here down to here, then you could do line. You could go here and make this the line instead of the top half of the parabola. Or if you're doing it Betty's way, you would go to here and just make this the line and make this the positive end of the parabola.
What if this graph, right? Didn't cross the exact Oh, gee, that.
Nothing different.
No, but I thought it was still be, I thought.
Oh, so that would be if like the parabola want to shift it down one.
Yeah, that's what I'm
So
saying.
if this whole thing is moved down one, so
Yeah,
like this point we're here.
So,
This is. I think this would still be plus or minus because we still have the top half and the bottom half, and then we would be taking the whole thing and moving it down.
Yeah, I thought it would still do the same. I mean, the points of intersection would change.